Hey guys, I am going to do the notes for the introduction to acids and bases. So, as I go through, I may have to do a little bit of drawing on here, but I hope you're fine with that. It'll probably be helpful for you. So, I can go ahead and click forward. Acids and bases are used all over the place, all the time. You have many acids and bases in your body. There's acids and bases all around you, and they're not always what you would think. Some things have acidic and basic character to them, even though they themselves aren't technically an acid or a base unless they get put in solution. So acids are in a lot of different food flavorings. Anytime you've ever had a soda, anytime you've ever tasted something sour, those are acidic substances. They have a pH that is less than 7. They produce hydrogen ions. And so examples of that would be lemon juice, vinegar, iced tea, soda, pretty much anything like that. Bases, on the other hand, taste bitter. They don't taste sour, they taste bitter. They are used in many cleaning products. They are also in foods as well. Their pH is greater than 7 on that 1 to 14 scale, and they produce a hydroxide ion. That OH ion is a hydroxide ion. Examples of bases that you would have run into are baking soda, ammonia, and bleach. Both acids and bases conduct electricity by producing ions. So what that means is when you throw an acid or a base into water, they're going to produce either the hydrogen ions or the OH ion, and that charged molecule in water allows electricity conductance. So an ion is really any charged particle, but when you throw those into water, they will conduct electricity. Water is considered a neutral molecule because it contains both hydrogen ions and hydroxide ions. So if you put this hydrogen ion right here with a hydroxide ion right there and bond them together, you get water, because that's what it is. It is both an acid and a base together, but those two things neutralize each other. An acidic solution is a solution that contains more hydrogen ions. So there's more of these guys, one or more of these guys alone. You might be asking yourself, well, how is that different than water? Water has those, yes, but it has an equal amount of H plus to OH, so it's still considered neutral and not acidic. If water were to have more of these hydrogen ions, then it would be considered acidic. Oops. And a basic solution contains one or more OH ions. So if you have those OH ions in abundance, you'll have a basic solution. So there are a few different models of acids or bases. There's the Arrhenius model, the Bronsted-Lowry model, and the Lewis model. So first thing I'm going to talk about the Arrhenius model. The Arrhenius model states that acids contain hydrogen and they produce hydrogen ions. So if we're taking hydrochloric acid, for example, that contains hydrogen, obviously it has a hydrogen in it, and when you throw it into solution so that it breaks up like this or dissolves, it's going to produce a hydrogen ion and a chloride ion, but the key one that you're looking for here is the hydrogen ion. Bases, on the other hand, contain hydroxide, and they're going to produce hydroxide ions. So this NaOH, sodium hydroxide, has that hydroxide ion within it, and when you throw it in water and it dissolves, it's going to produce the sodium ion and a hydroxide ion. It does not split up into sodium, oxygen, and hydrogen. The reasons for that have to do with electronegativity and KPAs and a bunch of different things that you are not going to learn about unless you take AP Chem or Organic Chem. The Bronsted-Lowry model, that states that acids are hydrogen ion donors and that bases are hydrogen ion acceptors. So that looks a little weird, so let me go ahead and explain. our acid, which you can see in purple, and this is just a pretend acid, HX does not actually exist, but it is going to donate a hydrogen ion. So in this reaction, this hydrogen ion, when this acid and water are reacting, this hydrogen ion ends up moving over there. And you can see that in the products because you see how this now, the water became H3O. So it took the hydrogen from the acid. So this is your acid because it's giving up that hydrogen ion. A base, on the other hand, according to the Bronsted-Lowry model, is a hydrogen ion acceptor. So this water, in this case, is acting as our base. Now, I know, again, you're probably asking yourself, but wait, you said that water wasn't an acid or a base. No, it's not. Water by itself is not an acid nor a base. However, it can play the role of one in a reaction by either donating a hydrogen ion or accepting a hydrogen ion. So in this case, this water here in this reaction is going to accept a hydrogen ion, becoming H3O plus. There should be a plus up there, but this water accepted that hydrogen ion. That's why the water itself is a base, and the acid over here, the HX, donated that. That's what makes it the acid. Over here, though, interestingly, on the other hand, if you were to do the backwards reaction, if this were to be an equilibrium, which it would be in a real life situation, and you were to go backwards, this hydronium ion, or the H3O plus over here, becomes the acid, because if you go backwards, it gives up that hydrogen ion, and then this X minus is the base in the backwards reaction because it's going to accept that hydrogen ion. So you see that happening backwards and forwards. In the Lewis model, on the other hand, acids and bases are either electron pair acceptors or electron pair donors. So acids in this case are going to be the acceptor of an electron pair. So in this first example, we see the hydrogen ion acting as an acid, because when H and F bond to one another, the hydrogen is going to accept an electron pair in that bond, and the base, or the fluorine here, is going to donate it. So I'm talking about bonding, which is something that we haven't talked about in a while. So let me just draw it out for you guys really quickly. So we have H plus, actually, let me draw it over there. Excuse me. Let's draw it over there. So we have this H plus, right? And this H plus does not have any electrons, because hydrogen by itself usually only has one electron, but if it's H plus, there's no electrons there. Fluorine, on the other hand, in neutral state, if you look at the periodic table, has 7 electrons. But you see this minus right here, meaning that fluorine has an extra electron right now. So if we draw our electrons, we go 1, 2, 3, 4, 5, 6, 7, 8, because of that extra minus right here, providing that extra electron. So we're seeing all of the electrons over here and nothing over there. So what actually happens during this is the fluorine is going to donate one of those electron pairs over to form a bond. So what you end up with over here is you end up with your HF bonded, just like that. And we have the others over there. And so it's donating that electron pair into the bond is what's going on right there. Making this the donor, this the acceptor, hence acid and base. So it's a little bit different to think about. For our BF3 over here, so boron trifluoride, we have our boron in the middle. We have 1F, 2 Fs, 3 Fs. Whoops, there we go, 3 Fs. And so we have our boron with its 3 bonds here. It's technically, it's okay right now. It's happy. It's not super unhappy at this current moment. And then we have our NH3 over here. H, H, and H. But our nitrogen over here has that extra pair of electrons. So in this case, I don't even have to draw out what the product looks like, because do you see this extra electron pair right here? That extra electron pair to be donated means that it can donate to the BF3 when that entire situation bonds together. And so you know this is the electron pair donor anyway, because you see the extra electron pair. And that makes the NH3 or the ammonia the base, and that makes our BF3 or our boron trifluoride the acid in this situation. So moving on, whoops, gotta erase all of this. All right. So now we are talking about conjugate acids and conjugate bases. Now this is a little bit challenging for a lot of people to look at a chemical equation and identify those, but just bear with me, I'll explain how to do that. A conjugate acid is something, we call it a species, but really it's a substance produced when a base accepts a hydrogen ion. So in this case, we are talking about what's going on in the products instead of what's going on in the reactant. And a conjugate base is a species or a substance that results when an acid donates a hydrogen ion. So it's the thing that forms in the product after the acid donated its hydrogen ion. And a conjugate acid-base pair are two substances that are related to each other by the donating and accepting of a single hydrogen ion. So what that means is if you have an acid that gives up a hydrogen ion, it's going to form a conjugate base. And if you have a base that accepts a hydrogen ion, it's going to form a conjugate acid. So here's the examples that I'll draw for you. So identifying the conjugate acid and base in the following. So let's go back to annotate so that I can draw a little bit. So if we're looking at this, the first thing we have to do is we have to identify the acid and the base here on the left. And I'm going to do this first example first, and then we'll move on to the second one. Looking at this, you want to identify your acid, and HF is going to be your acid. And you know that because HF has a hydrogen in it. It does not have an OH in it. And then over here, you can see that when you're moving towards the products, that F, it donated that H to something else. So this guy becomes your acid, which means that in this case, water is acting as your base because it's the only other option there. So now our challenge is to go ahead and identify the conjugate acid and the conjugate base. So if we recall from before, let's go back to the previous slide, a conjugate acid is something that's produced when a base accepts a hydrogen ion, and a conjugate base results when an acid donates a hydrogen ion. So looking at this, what that means to us is this acid is going to have a conjugate base, and this base is going to have a conjugate acid. So the thing that is related to this acid, and you know it's related to the acid because the main part of the acid, or the other part other than the hydrogen ion, still remains on the right, is this right here. So in our product situation, this HF donated its hydrogen ion to this thing over here. So when I said that this acid has a conjugate base, it means that whatever's left after the donation happens to be the conjugate base. Now, this thing, our hydronium ion, that is most closely related to our base. So when the base accepted that hydrogen ion, it became a conjugate acid. And the reason that that's a thing is because think about it in terms of equilibrium. Let's pretend for a second that this was going both ways. I'm going to change the color for a second. Let's pretend that the backwards reaction was happening. And these two things were what you added initially. Well, in that case, in the backwards reaction, this hydronium is going to donate a hydrogen ion to this thing, which is going to accept it. And if you're going backwards, this thing is your base and this thing is your acid. In the forward reaction, this thing is your acid and this thing is your base, but they have the conjugate opposite going on because remember, equilibrium situations exist. Okay, so let's go with green for this one. In this case, we have another situation going on. We have ammonia and water. So in this case, we have the ammonia here, which ultimately looks like it's accepting a hydrogen ion, and we have the water, which looks like it's actually ultimately donating a hydrogen ion. So in this case, the water is not acting as the base, the water is actually acting as the acid. And in this case, our ammonia is our base. Which, I mean, if you're familiar with ammonia, you know ammonia is a base anyway, so you could have identified that. But if you weren't, that's how you're going to look at these equations and figure that out. So the thing that forms after the base accepts the hydrogen ion, so this thing, that is your conjugate acid. And the thing that forms after the acid donates that hydronium ion, this is your conjugate base. Because once again, if we change the color back to red and we consider the backwards reaction, in this situation, if these two things are our reactants, this ammonium is going to donate a hydrogen to the hydroxide, forming water over here. So in our backwards reaction, this thing is acting as our acid, this thing is acting as our base. So don't ever forget the equilibrium situations exist, because if you do, then you're just going to end up confusing yourself. All right, so I'm going to erase all of that so we can move forward. Right. All right. And so our last slide is talking about amphoteric substances. Amphoteric substances are pretty easy to think about. They really just contain both hydrogen ions and hydroxide ions. So water would be the most popular example of an amphoteric substance. So you don't really need to know too much about amphoteric substances other than that they exist, and definitely remember that water is one of them, but just really know that they are a thing at this point. Other than that, if I can go back up here, I will stop the recording, but I hope that was helpful to you. If you have any questions, I will definitely do another a Zoom session so that I can answer any additional questions. Have a good day.